This video seems like sort of an easy breath of fresh air compared to the stuff we've been doing. It's referred to as the mean value theorem for integrals. That's the main result that we'll talk about in this lesson. But let me first start with the following. I want you to consider x bar, that equals the summation I equals 1 to n xi divided by n. We know this guy is the mean or the average. X bar is the average or mean of the x1, x2 up to xn. So what I want to try to do is create something of an analog for calculus, something that we can talk about for the mean value of a function. So we're going to try to create an analogous version of this. So the goal, create an analog to the average for continuous functions. So let's start as we normally do. Let f be continuous on the closed interval AB. All right, so we know the integral exists. So first, create the Riemann sums like we normally do. So a Riemann sum create a Riemann sum, I equals 1 to n, f of xi times delta x. And this I'm thinking right-hand endpoints would be fine. There would be no problem with it at all. So if we want the average, of f of x1, comma f of x2, comma dot 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 up to f of x sub n is same as the formula I gave before. I'm going to call it, do I want to give it a name yet? Not just yet. Summation I equals 1 to n f of xi divided by n. Now, if you remember, when we were doing delta x, when we did those all where they had the same exact thicknesses, delta x was b minus a over n. Let me fix that a. I want to use the same. It doesn't really matter what the n is, but that means I could rewrite where n equals b minus a divided by delta x. So that's what I'm going to do next. So this is the sum, I equals 1 to n, f of xi, all over b minus a divided by delta x. I'm going to simplify a little bit. The b minus a I can do anything with. I'll just pull it out front. 1 over b minus a, summation I equals 1 to n, f of xi delta x. So it leads itself perfectly to a Riemann sum. This part here is a Riemann sum. It doesn't really even matter if that's there. That's still a Riemann sum. Define f with a bar over it, so that's like the average value for f, equals the limit as n goes to infinity, 1 over b minus a, summation I equals 1 to n, f of xi delta x. And well, we know what this is since the function is continuous. Any kind of Riemann sums like this converge to, or the limit is the integral. So I'll put an f bar over there. This guy right here, f bar is the average value of f on the closed interval AB. So let's just do a few examples. Compute f bar for f of x equals 3 on the interval -7 to 5. So you could probably guess, since it's always 3, the average should be 3. Let's see if it works out that way. So f bar equals 1 over b minus a, so that's the b is 5. 5 minus the a is -7. The integral goes from -7 to 5 of 3 dx. That equals 1/12 times. The antiderivative of 3 is 3x, but we want to evaluate it from -7 to 5. Now I can do a little simplifying. For example, that'll be a 4, so I'll have x over 4. So I'll have 5 over 4 minus -7 over 4, which equals 5 over 4 plus 7 over 4. That equals 12 over 4, which does in fact equal 3. That should make sense. If the function is the same value throughout the whole interval, its average should be that. Let's try another one. Let's compute g bar for g of x equals cosine of x on the closed interval 0 to pi over 2. So g bar equals 1 over b minus a, so that's pi over 2 minus 0. The integral goes from 0 to pi over 2 cosine of x dx. This down here, this will be just pi over 2, but when you have it in the denominator like this, this will become 2 over pi times the antiderivative of cosine is positive sine of x, and that's evaluated from 0 to pi over 2. So we get, here's one thing you can do, that you can leave this 2 over pi out front, and then inside of here we could do sine of pi over 2 minus sine of 0. Then we have 2 over pi times sine of pi over 2 is 1. Sine of 0 is 0. So this equals 2 over pi. One last example. Compute h bar for h of x equal to x squared plus x plus 1 on 5 to 10. Closed interval 5 to 10. So h bar equals 1 over 10 minus 5. The integral goes from 5 to 10. X squared plus x plus 1 dx. This equals 1 over 5. The integral from 5... Actually, let me go ahead and do the antiderivative now. I think that's not a big deal. Let's see. The antiderivative of x squared is x cubed over 3 plus x squared over 2. The antiderivative of x is x squared over 2, and then finally plus x. And then we put this vertical bar, put a 5 to 10. Let's go ahead and plug those in and see what we get. Once again, I'll just have the 1/5 out front. And I think I'll use brackets this time because there's a lot of stuff going on here. Let's go ahead and throw the 10s in here. I'll have 10 cubed over 3 plus 10 squared over 2 plus 10 minus 5 cubed over 3 plus 5 squared over 2 plus 5. Now let's see what happens. I don't know if I want to do the 1/5. I think I'm going to leave that hanging around right now. 10 cubed is 1,000, so I have 1,000 over 3. 10 squared is 100, but over 2 is 50. Plus 10. Minus, now all these are going to be negative, so I have minus 125 over 3, minus 25 over 2, minus 5. Let me collect my things over 3 and stuff like that first. So I have 1 over 5, bracket. I can take 1,000 over 3 minus the 125 over 3 and end up with 875 over 3. Unfortunately, 3 does not go into 875. The whole numbers, I got 50 plus 10, that's 60. Minus 5 will be 55. And then I just have something over 2, minus 25 over 2. So I might as well go and get the common denominator of 6 and deal with it. So I have 1/5. So to get this over 6, I need to multiply by 2. So I have 1750 over 6. 55 times 6 is 330. And then 25 times 3 is 75. I don't know if I should... Now let's go ahead. I just feel like taking this 1/5 and multiplying it through right now to make all the numbers littler. Like this 1750 here, if you brought the 1/5 through, that would be, let's see, 300, and then I would get 250, 350 over 6. So 350 over 6 plus, interestingly enough here, if I divide this by 5, I'll end up with 66 plus 66 over 6. And then 1/5 here will be minus 15 over 6. And now let me go ahead and add them together. I'll get 350 plus 66 will be 416, 401 over 6. And that's as simplified as it's going to get. Now, while F bar is the average of F on AB, there is no guarantee that F bar equals F of X for any X. So there's no guarantee that the average value is actually an F value. Just like when you take the average of a bunch of numbers. Let me go back up to where I did the average for a bunch of numbers. Like when you take the average, a class average, for example. Let's say the class average on a test was 70. Nobody in the class had to get a 70. Whether it's even likely or not, it's hard to say. It depends on how many people were in the class. But we do have a little bonus here, and it's the mean value theorem. So let's do it. The mean value theorem for integrals. We had a mean value theorem, but that was differentiable version 1. So let me go ahead and write down what this one says. Let F be continuous on the closed interval AB. then there exists, let's put it that way, there exists C in the open interval a to b. That means C is strictly between a and b, such that f of C equals f bar. Proof. Let capital F of x equal the integral from a to x f of t, little f of t dt. Then what we know about f is this. Then capital F is continuous on the closed interval AB and differentiable on the open interval AB. Well, if you remember, I don't know if you remember the mean value theorem. Well, I'll tell you what, this is what you need. The regular mean value theorem for derivatives. You need the function you're going to deal with to be continuous on the closed interval and differential on the open interval. If that's the case, by just the mean value theorem, that's for differentiable functions, there is a C in the open interval AB with capital F prime of C equals capital F of B minus capital F of A all over B minus A. This is exactly what it says. The derivative function had a value at C there. Now we do already know that capital F prime is little f prime, is little f. So we know that little f of C equals, and this guy right here, capital F of B minus F of A, that is the integral. Let me take the 1 over B minus A out here. Capital F of B minus F of A is the integral from A to B, f of x dx. That's because capital F is an antiderivative. Or in other words, f of C equals f bar. Suppose the integral from a to b f of x dx equals 0. Well then, f bar, which equals 1 over b minus a times the integral from a to b f of x dx equals 1 over b minus a times 0, which equals 0. But by I'm going to use this notation, mean value theorem for integrals, by the mean value theorem for integrals, there is a C in the open interval AB with f of C equals f bar. What does that mean then? Well, thus, we'll make this the big conclusion thus. If f bar equals 0, well, better than that. I did more than just that. If the integral from a to b f of x dx equals 0, then f has a 0 inside of the open interval AB. As another example, find all values of c guaranteed by the mean value theorem for integrals. I'm going to do two functions. One, f of x equals 2 to the x on the closed interval 0 to 3. And then g of x will equal 1 over 1 plus x squared on closed interval -1 to 1. So let's take a look at these. Let's start with f bar. That equals 1 over 3 minus 0, the integral from 0 to 3, 2, not e to the x, 2 to the x, 2 to the x dx. Do you remember the antiderivative for 2 to the x? Remember, the derivative of it is 2 to the x times ln of 2. So you multiply by ln of 2. What do you do when you integrate? You divide by ln of 2. So this equals 1 over 3 times 2 to the x over ln 2. And I'm going to integrate from 0 to 3. So I'm going to take the 1/3 and ln 2 and put it together in front. 1/3 ln 2 times 2 to the 3 minus 2 to the 0. This equals 1. I think I'm going to make this ln 8, just be a little bit easier. Ln 8 times 8 minus 1. So we have 7 divided by ln of 8. Now, that f bar is supposed to be able to equal that somewhere. So, or f, we're supposed to be able to find an f of c that will equal that. Let's see here. F of c, well, I know that's 2 to the c, but I need that to equal 7 over ln of 8. So how would you solve something like this? I would probably take the natural logarithm of this thing. So I'll get ln of 2 to the c. I would do log base 2, but I think it would get messy. Equals ln. Is on every calculator. 7 over ln of 8. Look at that. And then I can take the c out front here, and I get c times ln 2 equals ln 7 divided by ln 8. And then I can divide by ln of 2. C equals ln, I might like writing it better, this 7 divided by ln of 8 divided by ln of 2. I wouldn't try to do much simplifying here. It's not really going to do you any good. What I do want to do is check to see if this is in fact in the interval from 0 to 3. I honestly can't tell you off the top of my head if it is. I might be able to do some estimating here. You know, like ln of 8, it might be around 3, then 7/3 is a little bit bigger than 2 ln. It feels like it's going to be in there, but let's go ahead and check it with a calculator. So I had, let's first make the division. Okay, enter. I had the natural log of 7 divided by, now I had done the natural log of 8, and all of that was divided by the natural log of 2. Now 0 to 3, 0 to 3, 0 to 3, give me the decimal version of that. Beautiful, it's about 1.75, so it is in, this is in the open interval from 0 to 3. So there's only one c guaranteed by the mean value theorem. The second function, g of x, g bar equals 1 over 1 minus -1, the integral from -1 to 1, 1 over 1 plus x squared dx. We all know the antiderivative for 1 over 1 plus x squared, and that is tangent, arctangent of x. We're going from -1 to 1. So let me go ahead and continue. I got 1/2 times tan inverse of 1 minus tan tan inverse of negative 1. And I end up with 1/2. Tan inverse of 1 is pi over 4. Minus tan inverse of negative 1 is negative pi over 4. And it looks like I'll have 2 pi over 4. I'll have 1/2 times 2 pi over 4. I can take this out and this out. That equals pi over 4. And pi over 4 is about 0.785. So that definitely is in the open interval from -1 to 1. One last idea, and that's it for this section, or this particular thing, involves even and odd functions. And if I'm going to let capital E of x be an even function, and I will let script O of x be an odd function. Throughout what I do here, I'm going to use that. So one of the things, it shouldn't really be a surprise when I write any of these things. What do we know about even and odd functions? We know that E of negative x equals E of x. Because of that, E is symmetric about the y-axis. So, I mean, any function, like, you could have some examples of E. You could have E of x equals x squared, or E of x equals cosine of x. I mean, any of these will all do that stuff. And if you look, how do they look on either side of the y-axis? They're identical on either side of the y-axis. Odd functions, on the other hand, have O of negative x equals negative O of x. And O is symmetric through the origin. So, what are some examples of these? Well, odd functions, odd degrees, obviously. So you could have like an O of x equals like x cubed. O of x could equal sine of x. You know, those are functions. When you look in quadrant 1, its mirror image is in quadrant 3. Or if you're in quadrant 2, its mirror image is in quadrant 4. So those are the two things we have. Some examples. If I do any of these things, say from -1 to 1, x cubed dx, what's going to happen? Well, I'll have x to the 4th over 4 from -1 to 1. That'll equal 1 to the 4th over 4 minus -1 to the 4th over 4. That will equal 1/4 minus 1/4, which will equal 0. The reason why that's so, if you look at the function itself, I'm going to have to try this again. That didn't work out. There we go. This is cute. I have not tried that thing before. All right, what happens is you have the function comes in here like so, and then comes up like this. And then if you look from 1 to -1, -1 to 1, if you consider these areas, you have negative area that just wipes out the positive area. I mean, anything that I do like that, like let's look at another one. The integral from -pi over 2 to pi over 2 sine of x dx, that equals, the antiderivative of sine of x is negative cosine of x. And cosine of x That's our negative cosine of pi over 2 minus negative cosine of negative pi over 2. Let's see what all that is. It really is not going to matter because this is going to be negative 0. This will be plus cosine of negative pi over 2 is 0. Well, it equals 0. So in general, if O of x is continuous, then the integral from negative a to a O of x dx equals 0. That's because stuff to the left of the y-axis cancels with the stuff on the right of the y-axis. One last example. Let's take a look at the integral from negative 1 to 1 of 1 over x dx. Now, this is an odd function. If you look at the graph of the thing, let me have this thing again. I like this little thing. That is sweet. All right, if you look at the graph of the thing, it goes like this. It's, how would you call it? A hyperbola, that's right. So if you try to do this, you're going to do ln, absolute value of x, and then you're going to go from negative 1 to 1. That's going to equal ln, absolute value of 1, minus ln, absolute value of negative 1. That's ln of 1 minus ln of 1. ln of 1 is 0. 0 minus 0 equals 0. So it looks like it's still going to work. The problem with it is that this guy right here, this integral, unfortunately, this integral does not exist. The reason why is because of the unboundedness. If you tried to do any kind of a Riemann sum here, remember, any kind of a Riemann sum, meaning that you could partition it any way you want. Imagine trying to partition where one side of the rectangle was the y-axis. Well, how tall are you going to make this rectangle? It has to be infinitely tall or infinitely deep also. Since the function is unbounded, this is unbounded. So the integral does not exist. So the point I'm making here is that you can't even begin to start a Riemann sum there because you'll get crushed when you if you try to do any Riemann sum that involves the y-axis being part of a rectangle. You can't make them. Let's continue on. As an example, let's do negative pi over 2 to pi over 2 cosine of x dx. The antiderivative of cosine of x is sine of x. And we're going from negative pi over 2 to pi over 2. Well, that equals sine of pi over 2 minus sine of negative pi over 2. Well, sine is an odd function, so this is 2 times sine pi over 2, which equals 2. Now, consider the integral that just goes from 0 to pi over 2. Cosine of x dx, same deal as before. Now it's going to equal sine of x from 0 to pi over 2. That'll equal sine of pi over 2 minus sine of 0. That equals 1 minus 0 equals 1. Okay, so the first integral was 2, the second integral was 1. So far, so good. Let me do another example. And then I'll tell you what this is all about when I do it. When I do this one, I'll tell you what I'm getting at. Let's do negative 2 to 2, x to the 4th plus x squared plus 1. If all the powers are even, then the function is even, because when you plug negative x in for x, it gets eliminated because of the even power. This is going to equal x to the 5th over 5 plus x cubed over 3 plus x from negative 2 to 2. Notice how the integral of an even function is odd, and I'll bet the integral of an odd function is even. I haven't checked that out completely, so got to be careful what I say, but I think I'm right. Anyways, let's throw these numbers in. We're going to have 2 to the 5th over 5 plus 2 cubed over 3 plus 2 minus negative 2 to the 5th over 5 plus negative 2 cubed over 3 plus negative 2. Notice, because they're odd, all these negatives can factor out, and I can simply get rid of them. This equals 32 over 5 plus 8 over 3 plus 2 plus, I'm going to write it again, 32 over 5 plus 8 over 3 plus 2. I'm not going to finish it, but I am going to do the integral from 0 to 2 of the same thing, x to the 4th plus x squared plus 1 dx. That will equal x to the 5th over 5 plus x cubed over 3 plus x from 0 to 2. And I'm going to end up with 2 to the 5th over 5 plus 2 cubed over 3 plus 2. And then the minus, once you plug in 0 for x, I'll have minus 0. I don't care about that part. Look at what I have. I'll do one more step. 32 over 5 plus 8 over 3 plus 2. So if you look at this, I have one of them here. I have two of them here. In all cases, you saw that in both of these examples, you could see that the value of the original function is twice that of the second function, of the one that only starts at 0, 2 to 1. Over here, when I do the original from negative 2 to 2, I get this number, whatever it is, times 2. And over here, I get that number, whatever it is, times 1. So this really shouldn't surprise you. If e of x is continuous and even, well, we already know that part, then the integral from negative a to a of e of x dx equals 2 times the integral from 0 to 2 of e of x. That looks like an English pound sign. E of x dx. That's not that huge of a thing, except you'll find when you're doing integrals, many times it is much more desirable to start at 0, because look over here. It's beautiful when you have a 0, because when you plug it in, it just zeroed out the whole thing. I didn't even have to worry about that particular computation. So that's a big deal. Sometimes it's not such a big deal. Like here, I mean, to me, I'm making it seem like it's a big deal, but this particular example is not the greatest one in the world. If the computations were incredibly arduous, this usually will be a much nicer computation to do than both of these. And I'll tell you what else too. These cause students the most ridiculous amounts of error because they lose track. They don't put parentheses around this thing, or they don't put parentheses around the negatives when they substitute them and things like that. An arithmetic error ruins their integral. So this is not so desirable, especially when you get a little bit good at these things. Many people will start to try to do this part in their head, and that is asking for trouble. Don't do it.